Have a look at this SAT question. It is very hard. You probably recognize the type. You are given one or two equations with one unknown constant, and your task is to determine the value of the constant that will give the equation, or system of equations, 0, 1, or 2 solutions. This question variant is one of the most common question types on the SAT, and I guarantee you that you will see 1 to 2 questions like this in your next real test. Some are trivially easy, some less so, but they're all very learnable. So it's critical you know how to solve these super quickly and super reliably. In this video, I'm going to show you exactly how. We'll start from the very basics and move on quickly to much harder variations, like the teaser from the start of the video. We'll focus specifically on the quadratic version of this question type rather than the linear type, which I'll be covering in a separate video. Over time, I promise we will do our best to put everything I know on YouTube for free. Ultimately, our goal is to provide you with the most in-depth and clearly explained SAT content available anywhere on the platform, because I strongly believe that the details matter. So we're going to take our time and do things right. But if your next SAT is right around the corner and you don't have time to wait around for another video to drop, you should check out our regular webinars. Each session will take a deep dive into a particular question type or topic that is super important to master for your upcoming SAT. We'll look at multiple variations on the concept, starting from very easy and ratcheting up the difficulty bit by bit until we get to the kind of questions that ruin an 800. Yes, just like we do in the videos on this channel, but live. So you can ask me questions directly and I'll clarify everything for you personally in real time. So if you like our videos, you will love our webinars. Links are in the description. And of course, like and subscribe. It is very, very helpful. Okay, back to the main show. There are two broad approaches to solving these questions: graphing the functions on Desmos with sliders and solving for the constant using the discriminant. The first is easier than the second, but sliders don't always work that well. So if you're aiming for a top score, you're going to need to learn to use the discriminant. Before we jump into that though, we should define what we even mean by solutions. A lot of students seem to get confused here. And it's understandable. The term solution can, somewhat confusingly, be used in three ways: a solution to a single equation, to a single function, or to a system of equations. Let's take these one at a time. First up, solutions to single equations, which hardly needs an explanation, but anyway, here it is. Given an equation in x, the solution to that equation is the value or values of x that make the equation true. For example, in this super hard question, 10x equals 20, the solution is, you guessed it, 2. Because that's what makes the left-hand side of the equation equal to the right-hand side. Simple linear equations typically have just one solution, but quadratic equations like this one, x squared equals 16, often have two solutions. In this case, we can square both -4 and 4 to get the same result of 16. So this equation has two solutions: x equals -4 and x equals 4. But not all quadratic equations have two solutions. The equation x squared equals -16, for example, has no solutions, because no matter what value of x we punch into the equation, the result will always be positive, or at the very least 0. So this quadratic equation has no solutions. And there's one last situation, which is this equation here, where x squared equals 0. In this situation, there's only one value of x that satisfies the equation, and that's 0. So this equation has just one solution. To recap then, quadratic equations can have 0, 1, or 2 solutions. Moving on to functions. A function is like a recipe. You take an ingredient x, do a bunch of stuff to it, and you get some specific result, which we call y. All of the following are functions. In the first, you put in x and get the same number out. In the second, you put in a number, multiply it by 3, and add 7 to get your output. In the third, you put in a number, square it, and add 5 to get your output. We can also write functions using f of x notation, where x is the input and f of x is the output. So these functions are all, respectively, equivalent to these. Okay, so we know what a function is now, but what on earth do we mean by a solution to a function? In the function y equals 3x plus 7, there are two variables, x and y. So what are we even solving for? It's very simple. When we want to find the solution or solutions to a function, we simply set y equal to 0 and then solve for x, just like we do for a single equation. And this same principle holds true for f of x notation, but instead of setting y equal to 0, we can think of the solutions to a function as being where f of x equals 0. You might be thinking that it's super random to set y or f of x equal to 0, and it is indeed a somewhat arbitrary definition. But there is at least some rationale for this, which becomes more obvious when we consider the idea of solutions to a function on the xy plane. If the solutions to a function are where that function is equal to 0, that is to say where the y value of the equation is 0, we can easily see the solutions on the graph, here and here, as the places where the curve cuts the x-axis, also known as x-intercepts. And it doesn't matter what type of function we're talking about either, the solutions will always be where the graph crosses the x-axis, like in this cubic function with 3 solutions here, here, and here, as well as this rational function with just one solution right here. In the context of a single function, we can actually use the terms solutions and x-intercepts interchangeably, which can also be referred to as the zeros and roots. The third way we use the term solution is to talk about where 2 or more equations are true for the same values of x and y. In the system here, there are 2 solutions. The point -1 and 0 is a solution, because if we plug that point into both equations, each one produces a true statement. -1 squared minus 1 is equal to 0, and 1/2 times -1 plus 1/2 is also equal to 0. And in this particular system, there's another solution at the point 1.5, 1.25, which also produces a pair of valid equations if we plug our point into our system. 1.5 squared minus 1 equals 1.25, and 1/2 of 1.5 plus a half also equals 1.25. We can also think of our system graphically. Since both of our equations include exactly 2 variables, x and y, we can graph the 2 equations, and the solutions will be the intersection points of the 2 graphs. In this system, the parabola drops down, approaching the horizontal line, but the 2 functions never meet, so this system has no solutions. In this system here, the quadratic drops below the horizontal line, creating 2 points of intersection, one here, the other there, so this system has 2 solutions. And in this system here, the parabola drops down and just barely touches the line before rising again to infinity. So this system has exactly 1 solution right here. When a straight line just touches a curved function like our parabola but doesn't actually cross it, we say the line is tangent to the curve. For any given quadratic function, any line that is tangent to the curve will produce a system with exactly 1 solution, like this system here, this one here, and this one right here. Okay, now that we know what we mean by solutions, let's jump into some real SAT questions. Let's start with this super simple question right here. This question is trivially easy to solve with Desmos. You simply type the equation into the graphics calculator, omitting the 0, and see how many times the function has crossed the x-axis. Why do we omit the 0? Because when we do so, Desmos treats the expression as a function and graphs a nice looking parabola. And since we want to know where our function equals 0, we simply check the x-intercepts, which, if you recall, is where y equals 0. Since the parabola crosses the x-axis twice, the equation has 2 solutions. So that's answer A, and you're done. Let's look at another example. In this case, the function doesn't already equal 0, but no need to panic. All we have to do is split the equation into 2 functions, setting y equal to the left-hand side and y equal to the right-hand side. This converts our single equation into a system, which allows us to see exactly where these functions cross, if indeed they cross at all, which in our case, they do not, and you're done. And yes, you're right, you don't really have to do this because you can't take the square root of a negative number, so this equation obviously won't have any solutions. And yes, if you can spot that in the real test, just answer D and move on. But things won't always be so obvious. Have a look at this example here. If you're just getting started with the SAT, then this unknown constant t probably looks a little nutty to you. But honestly, you've already learned everything you need to know to answer this question. The key, once again, is to treat the left and right-hand sides as separate functions. So instead of this, we create 2 functions with y equal to the left-hand side and y equal to the right-hand side. Okay, fine. But we still have that unknown constant. What are we supposed to do with that? Well, once you've entered your equations into Desmos, you just create a slider for t by typing t equals 1 into the next line, and you can now use your slider to test out different values of t. Since this question is multiple choice, we really only have 4 options to test out. Option B produces a system with two solutions, as do answers C and D, while answer A produces no solutions because the two lines never touch. So our answer is A. But what if we don't have answer choices? Let's look at this example here. The process is basically the same. We enter our two functions into Desmos, create a slider for the unknown constant k, and look for the lowest possible value of k that will produce no real solutions. But this time, since we don't have answer choices, we need to find that value ourselves. And if you read too quickly, you might wind up zooming in closer and closer, trying to get the parabola as close as possible to the horizontal line without actually touching it. But every time you zoom in, you see that you can get closer still, and on, and on. What you missed here is that k can't be any old number. It must be an integer, a whole number, in other words. With this additional constraint, the closest we can get to the horizontal line without touching it is where k is equal to 14. If we go lower to k equals 13, the lines cross and the system has two solutions. You can even restrict the slider to only allow whole numbers, which reduces your cognitive load and prevents you from accidentally losing your mind and forgetting to choose an integer, thereby screwing up a problem that really should be trivially easy to solve, especially now that you've got this super simple stuff on lock, right? Where things can get a little trickier, however, is when the question asks you to find the value of a constant that gives the equation, or system of equations, exactly one solution, and you don't have any answer choices to limit your search space. A problem like this one, for example. In this problem, finding the exact spot at which the two curves just touch is tricky. Notice how annoying it is to get the curves closer and closer together. We can adjust the slider's bounds, narrowing the gap between minimum and maximum, and eventually we'll get to the right answer. But clearly this approach on this particular question is not good. So how do you know when the slider will work well? Ask yourself two quick questions. Are there answer choices? And two, does the constant have to be an integer? If you answered yes to both of these, the slider is a solid approach. If not, ask yourself one last question. Are there fractions in the equations? If yes, the slider may or may not be effective. It might still work, but there's a chance it drags you into decimal hell. In these cases, you'll need another approach. Many of you will already be familiar with the discriminant, b squared minus 4ac, and how it can be used to determine the number of solutions to a quadratic equation or function. What only a few of you will know, however, is how to apply this idea efficiently in the real SAT. And if everything I just said was total gibberish, don't worry, I'll be explaining exactly how this all works right now. So either way, keep watching, I promise you will learn something. But before we jump into more SAT questions, I want to take a minute to briefly explain how the quadratic formula works. This is the quadratic formula as you have memorized it. And assuming you actually have memorized it, you probably know that its purpose is to produce the solutions to any given quadratic in the general form, ax squared plus bx plus c equals 0. At first sight, it is a rather hideous thing, but it is a helpful tool because no matter what quadratic equation they throw at you, no matter how ugly the values of a, b, and c, the formula will find the solutions if they exist. But yeah, it's not pretty, and it's not especially intuitive. And as a normal, well-balanced human, you probably don't know how on earth the different components of this formula relate to a particular parabola. This is completely normal, because this formula is hardly ever explained thoroughly in your usual math classroom. In this video, I won't be explaining it thoroughly either. We'll save that for another sweet, glorious day, but I will explain how it works from a very high level, because it's actually more expressive than it seems. For starters, if we split the fraction, we get this, which allows us to consider what each piece means individually. The part on the left, minus b over 2a, shows us the parabola's axis of symmetry. If you picture a parabola, its axis of symmetry is the vertical line going right through the parabola's vertex, cutting the parabola in half. When you calculate minus b over 2a, what you get is the x value of that particular line. And to get to the solutions, we have to take some number of steps from the axis of symmetry to the left and to the right. Enter the discriminant. If that value under the root, the discriminant in other words, is positive, we'll get one solution some distance to the left of the axis of symmetry and another the same distance to the right. But if that discriminant is equal to 0, then the solutions are 0 steps from the axis of symmetry. So both solutions, in other words, will be exactly at the axis of symmetry. And when the discriminant is less than 0, that would require us to take the square root of a negative number, which isn't possible, at least not in the real world. To summarize then, here are the only three possible scenarios. Given a quadratic in the form ax squared plus bx plus c, the discriminant, often shortened to the capital delta, tells you how many real solutions exist. When delta is negative, the quadratic has no real solutions. When delta equals 0, the quadratic has exactly one real solution. When delta is positive, the quadratic has exactly two real solutions. Using the discriminant to determine the number of solutions to a quadratic function can be a much more reliable method for solving SAT questions like this one. Yes, you could use the slider here as well, but the discriminant is just as quick. We want one solution to this equation, so the discriminant should be equal to 0. Our a value is -9, b is 30, and c is unknown. So we punch these into our formula to get 30 squared minus 4 times -9 times c equals 0. If this looks like a pain in the ass to solve from here, you've probably forgotten that Desmos is amazing at solving this sort of equation. Just type the equation into Desmos, replacing the equals sign with a squiggle, and you are done. Which is pretty fast and very reliable, because it allows you to cut straight to the answer without guessing, checking, and possibly losing your mind, fiddling with the slider while the clock is ticking. But there's a little more to it. Because what happens when the equation isn't already in the general form, ax squared plus bx plus c, like in this problem from earlier where the slider fell short. Here we even have two equations. So what do? If you've been paying attention, you'll recall that you can split equations into two halves, y equals the left and y equals the right, to better see their solutions on the xy plane. Well, guess what? We can also do the same thing, but backwards, combining the two equations into a single equation to produce a single quadratic function. In this problem, both our equations are equal to y, so we can simply equate them and put our equation into the general form to calculate our discriminant. Now we just need to figure out what our a, b, and c values are. A and b are easy, 1 and 4 respectively. But a lot of students get tripped up by the k plus 23/7 part. How are you supposed to know which is C? Don't worry, this is actually easy to figure out with a simple example. Imagine you had this quadratic. Obviously, in this example, C is 11, right? Well, would that change if I arbitrarily split the 11 into 7 and 4 like this? Hopefully you can see that our C value is the 7 and the 4 together, because what we're interested in is the whole value of the whole constant term at the end. Similarly, if you have this equation, the C value will be the whole constant term together, with all of the bits that make it up. So in the simple case above, C is 7 plus t. In our problem, therefore, with the quadratic 0 equals x squared plus 4x plus k plus 23/7, the value of c is k plus 27/7. We now have our values of a, b, and c, so we can calculate our discriminant, set it equal to 0, and solve the resulting equation. And this is precisely where Desmos regressions shine. Instead of fiddling with the slider or worrying about dealing with awkward decimals, the regression produces a precise value for k, which allows us to type it into the next line and click the fraction button. So our final answer is 5/7, and we are done. But what about when we want to find a value of a constant to produce a system with 0 or 2 solutions, like in this problem here? We could of course use the Desmos slider method in this question, but there's a way to do it with the discriminant too. All we have to do is type our discriminant to Desmos as we did before, but this time instead of setting our expression equal to 0 to produce an equation with one solution, we set it to be less than 0 to produce an equation with no solutions. The problem is that entering the discriminant into Desmos this way doesn't work. Desmos simply offers us a slider for b, a slider that does precisely nothing. But if we use x instead of b, something changes. The xy plane changes color, and if you zoom out a little, you see that Desmos has plotted two dotted vertical lines here and here. But what does this mean exactly? When we plot an inequality in Desmos, the software will shade in all the x values on the graph that make the given inequality true. So in our case, the shaded area shows all the values of x where the inequality x squared minus 4 times -1 times minus 676 is less than 0 is true, which is where the quadratic has no solutions. In other words, any value of x, which is our b value in the discriminant, mind you, that is greater than -52 and less than 52 will produce a discriminant that is less than 0. The values -52 and 52 themselves represent where the discriminant is equal to 0, and all the values below -52 and greater than 52, the unshaded area that is, will produce a quadratic with two solutions. You might be thinking, why bother? Why not just use a Desmos regression to find the value of b where the discriminant equals 0? Then just take the closest integer just below that value. For most of you, it won't be immediately obvious whether you need to take an integer above or below your result. Does b need to be bigger or smaller than 52? And what about the other value of b, negative 52, that also produces exactly one solution? Does that change things? And will you even know there's a second value of b that produces a parabola that only touches the x-axis once? These are not the sorts of questions you want to be asking yourself in the middle of your SAT. What you want instead is a bulletproof method that is fast, robust, and intuitive. This method is also particularly helpful when your b value, or a constant within your b value, is unknown. Desmos regressions are great, but their one hard limitation is that they can only find one solution to a given equation. So when you're trying to solve for b in the discriminant, you may well run into problems, because the b value is squared, which will always result in two possible values of b. And because a Desmos regression only solves for a single value, it may not solve for the value that you need. Have a look at this example. Here we've got no answer choices, and we've got this potentially annoying fraction of 1/7. And sure enough, if we try using the slider, we run into trouble. For one, the graph is pretty hard to read. The linear function here has a pretty steep gradient, and even if we zoom in, we quickly figure out that k is not going to be a pretty little integer. So we go to our discriminant method. We rearrange the functions to create a single quadratic, like so, and now we can use our discriminant. But wait, what are our values of a, b, and c? The values of a and c are pretty clearly 4 and 25, sure, but this time our b value isn't so obvious. Just like before, we need to remember that the b value is basically a count of all the x terms. Consider these three quadratics side by side. In the first example, b is obviously just 7. In the second example, the b value is also fairly obviously 7 because we have to add the two x terms together before determining what b is. And the same is true for the third example. We must sum up both x terms, which together make 5 plus k. So back to our problem. In our case, we have two x terms, negative k and 1/7. We add these together to get our b value of 1/7 minus k, and we're ready to use our discriminant. The next step is to solve for k. You might be thinking, let's just use a Desmos regression, but this doesn't quite work. Entering this into Desmos and replacing the equal sign with the squiggle, like so, gives us a possible value for k, 141/7, which is wrong, because our problem stated that k must be negative. And this is where our other approach comes in. If instead of running a Desmos regression, we replace the unknown k with an x, Desmos will find all values of x that satisfy the equation. In this case, we see there are two solutions. There's the positive value k, 20.14286, which is what we got with the Desmos regression, but there's also a negative value, k equals negative 19.85714, which is the one we want. There is in fact a way of salvaging the regression, but it doesn't always work. Still, I think it's worth mentioning because when it does work, it's quite clean. When you've entered your equation into Desmos and replaced the equal sign with the squiggle, you simply add a curly brace, write in your condition, in our case that k should be less than 0, and Desmos should, at least in theory, only search for values of k that are less than 0. What's nice about this is that we can now enter that constant into the next line and click the fraction button. Doing so produces the fraction minus 139/7, which may seem like an ugly fraction to you, but it is indeed the right answer. It's rational, for one, and the fraction fits into the 5 boxes provided to you in the student-produced response input field. Okay, up next, hidden quadratics. So far, every problem we've seen has fairly obviously been about quadratic equations and functions. But you will very likely encounter variations on this question type that are a little harder to spot and a good bit harder to solve, even if the basic techniques and concepts remain the same. Have a look at these two problems. In many ways, they look completely different. The first is a radical equation, while the second, the teaser from the start of the video, is a rational equation. And yet, as you'll soon see, with a bit of rearranging, they can both be transformed into quadratic equations like those we've already discussed in the video. But how can you tell? Let's compare them both to this vanilla-flavored question from earlier. All three, despite the variation in the structure of the equations, have almost identical sentence structures. Each question presents an equation with an unknown constant, states that the equation has 0, 1, or 2 solutions, and requires you to solve for the unknown constant. Okay, fine, but why does this mean that the two weird-looking ones are actually quadratics? Well, simply put, the SAT is a simple test, so anything more complex than quadratics for this type of question would be outside the scope of the SAT. These equations, therefore, no matter how complicated they may look, will always be fairly easy to transform into a quadratic, and from there you just apply the rules and techniques from earlier in the video. Okay, back to this first example, the one with the radical. We want to find the value of 4k, given that the equation has exactly one solution. As always, we have two options. First, plot the equation as two functions and use a slider. Second, convert the equation into a quadratic and use the discriminant. We'll start by plotting the equations. By now, you should have these steps on lock. You just have to plot y equals the left and y equals the right. Then you fiddle with the slider until the two curves touch exactly once. Just like in the examples at the start of the article, the system will have one solution when the linear equation is tangent to the curve. Notice that as we slide k higher and higher, the curve moves closer and closer to the linear equation. We're clearly going to need a bigger value than 10, so we raise the upper bound on the slider to say 100, and we drag until we're closer to our target. Now we can see that we're not quite touching it when k equals 38, and we've gone too far when k equals 39. So the correct value is somewhere in between. Adjust the lower and upper bounds of your slider, setting the minimum to 38 and the maximum to 39, and now you've got super fine control. Zoom in a little more, and you see that the linear equation appears to be tangent to the curve when k equals 38.75. Now you just type in 4k into the next line, and presto, there's your answer, 155. Not bad. But again, what if the correct answer was a more awkward fraction, something like 41/81 or 17/23? It worked out fine this time around, but if it hadn't, you might find yourself, once again, in decimal hell. So let's try it with the discriminant. Here, the main challenge is to get this equation into a quadratic form. We don't like that square root, so let's square it. That very helpfully converts the left-hand side into a linear and the right-hand side into a quadratic. Now we do a little cleaning up to get a single quadratic in the general form. This is probably where most students spend most of their time and make most of their mistakes. In particular, it's this step here, expanding 39 minus x all squared, where people waste a bunch of time and often forget to include the middle term. Wouldn't it be nice if Desmos could expand brackets for you? Well, it's your lucky day. When you get to this point here, you simply type your quadratic expression into a new line. Click the cogwheel in the top right corner of the input panel, and click the table icon next to the expression. This generates a table of values, and you can now run a quadratic regression, which transforms your factored quadratic directly into the ax squared plus bx plus c form. And we can now use our discriminant just as before. Entering this into Desmos produces the result that k equals 38.75, and we now simply enter 4k into the next line to get, once again, 155. So, which approach is best here? Probably the first, even with the risk of hitting some weird numbers. And here's why. It doesn't take much time to move the slider around, and if it fails, you can still use what you've already typed into Desmos when you move to your backup plan of using the discriminant. All you have to do is delete your slider and calculate the discriminant. And when Desmos defines k with the regression, it also defines it in your system of equations above. If your value of k is correct, then your linear equation should be tangent to the curve. If you've blundered somewhere along the line, however, like forgetting to flip the sign when you move the negative x to the right to incorrectly get negative 79x instead of negative 77x, the resulting graph will make it obvious that you've erred somewhere along the way. Solving the discriminant with these incorrect values will yield a result that k equals negative 39.25, which produces a linear equation that is miles away from our curve. So something is clearly rotten in Denmark. Okay, final question. Kudos for making it this far. Here's our second example of a hidden quadratic. Just like for the previous question, we're going to compare our two approaches, using a slider versus using the discriminant. Let's start with the slider again. By now, this should be automatic. Split the equation into two halves, plot each side into its own Desmos line, create a slider for c, and move the slider around to make the linear equation tangent to the curve. But we have got two problems. For one, the resulting graph is very hard to read. No matter which way we move the slider, our graph is super squished. And what we can see isn't particularly helpful. We're looking for a value of c that produces exactly one solution. But by the looks of it, every value we test seems to produce one point of intersection. Luckily, there's a way to salvage this approach. But before I spoon feed it to you, let's try to think about why this graph is hard to read. Let's consider each function separately. The first function, our curved one, is a rational function that bends inwards in two spots, here and here. And the second function is actually just linear, with a slope of 1 over 124. Let's imagine for a second you could draw any straight line on the graph that you like. If you wanted that line to not touch the curve at all, you'd place the line here between the two bendy bits. If you wanted to give the system two solutions, you'd draw the line so that it cuts straight through one of the bendy bits. And if you wanted one solution, you'd place the line right up against one of the bendy bits so that the line and the curve touch at exactly one spot. So why doesn't our graph look like this? Well, it actually does, but we can't see it because our slope is so small, which squishes everything together and makes it impossible to see what's actually going on. Unfortunately, we can't change our slope directly, but what we can do is stretch the graph out along the vertical axis. Just place your mouse over the y-axis, hold the shift key down, and zoom in and out. You should see the y-axis stretch or compress, depending on which way you zoom. See how the graph gets a little easier to read as you stretch out the y-axis? Just keep going until the linear equation looks to be rising at about a 45-degree angle. And you can now go back to fiddling with the slider. Making c less than 0 flips the curvy bits, and it appears that as c gets smaller, the line approaches the spot where it will be tangent to the curve. And at -31, we have arrived. Pretty easy if you know the trick with the axes, and if you think to use it. And those are two very decently sized ifs. Perhaps the discriminant is easier? Here, the main challenge is converting this rational equation into a quadratic. One way or another, we're going to need to get that x out of the denominator. Let's compare three approaches, two not so good, and one a little cleaner. Okay, ugly method number one. You've got these two fractions here, so why not combine them into a single fraction by finding a common denominator? With these fractions combined, you cross multiply and move everything over to one side. Now that you've got an equation in the general form, you punch your a, b, and c values into the discriminant to solve for the unknown constant. But this fails miserably because c is not 0. Why has Desmos betrayed us in our most desperate moment? Well, in this case, because the constant c appears in every term, Desmos rightfully believes that c equals 0 is a solution. But 0 doesn't work because making c equal to 0 would mean our original equation contains division by 0, which breaks math. And never break math. But wait, what about our sneaky trick with the condition from earlier? Can we add some curly braces that ensure c is negative? You can, but that fails too, for reasons somewhat incomprehensible to me. And no matter what condition we add, we just keep getting garbage output. Not good. So back to the drawing board. The second not so great approach does start with a clever realization that to turn this equation into a quadratic, we technically only need to multiply both sides by x. Already here, the algebraic manipulation is much cleaner. But when we punch this into the regression, it gives us another wacky answer. Why does Desmos mess this one up? Honestly, I'm not entirely sure, but it definitely has something to do with the unknown constant in the denominators here and here. And again, adding a curly brace condition doesn't help. So once again, back to the drawing board. With these types of rational equations, the best approach is usually to find a common denominator for all three fractions simultaneously. In our case, that common denominator must contain 124, c, and x, so we convert each fraction by adding the missing components to the numerators and denominators, and we can now cancel out the denominators of all three fractions in one very satisfying step to get a nice flat equation. The algebra is pretty clean, and our result doesn't include any superfluous c values. But will it blend? We type our a, b, and c values into the discriminant, set it equal to 0 with a squiggle for an equal sign, and yes, thank God, this approach appears to work. But the whole experience has been unpleasant. What happens if your regression breaks on you mid-test? Will you really know what to change in your form to bring it to heel? Maybe, maybe not. But there is another way around this problem of the broken regression, and we've already seen it in the article. All you have to do is swap out the constant c for an x, plot the equation, and Desmos will plot vertical lines at the solutions. This approach works for all three versions, so it's clearly pretty robust and a critical trick to have in your bag when things go awry. Okay, let's wrap things up. We clarify what solutions mean for equations, single functions, and systems. They correspond to values that make an equation true, to x-intercepts for a function, and to intersection points for systems. We then developed two complementary approaches to count and locate solutions in quadratic settings. Sliders on Desmos are quick and visual, and often enough when answer choices are provided or when the constant is an integer. But beware. Fractional coefficients and squished graphs can make sliders fiddly. You can always narrow your bounds and squeeze or stretch your graph along the y-axis to make the graph easier to read. Next up, we looked at the discriminant, b squared minus 4ac. When the discriminant is positive, the quadratic has two solutions. When it's equal to 0, you'll get exactly one solution, and when it's negative, you'll get no solutions at all. The discriminant is more robust and precise than using a Desmos slider, but it does require you to rearrange the equation into the general form first, which can be time-consuming and may not even be necessary if the slider works well first. Where this method really shines, however, is when constants are non-integers, when you need exact thresholds, and when the numbers in the problem are very big or very small. But beware, Desmos regressions can be fragile. If yours breaks, revert to a graphical solution with x as your unknown. Lastly, we saw that many non-quadratic looking prompts, radicals, rationals, can be rearranged into a quadratic in x, at which point the same discriminant logic applies. For radicals, isolate and square with care before consolidating into the general form ax squared plus bx plus c. For rationals, give all terms a common denominator before canceling out all the denominators in one fell swoop. It might seem like a lot, but the truth is that pretty much every student I've ever worked with has gotten very fast at applying these ideas in the real test. What I recommend is that every time you practice these questions, you try both approaches, and soon enough you'll develop an intuitive feel for which method to use under which circumstances. Honestly, all it takes is a couple of hours of focused practice, and soon enough you'll be whizzing through them, guaranteed. And lucky for you, we've put together a free worksheet for this exact purpose. The worksheet contains questions for this exact type, with a good mix of difficulty levels and structural variations. Okay, that's it for now. I promise we'll try to put out more videos more regularly. But if you're eager to get started, remember, we run regular webinars, links in the description. Until then, good luck with your prep, have a very good day, and thank you so much for watching. See you in the next one.